So these are the due dates for the, where is it? Yeah. So these would be the due dates for experiment. The experiment number 1 will be due 3rd September, which is this Friday. And then it's like every Friday we have the submissions. So September 10 is the experiment number 2, which is what we will be discussing today. And, and so on. 12th November is our last experiment. I think the mid-sem is from 13th to 18th September. And the end-sem is after, I think, some 18th November or something, I guess. Or 18th November is the last day of class. There is a recess in October, I think from 10 to 17 or something. So I have taken care of those. So these are the due dates for the experiments. The first one will be due this Friday. Any question, comment here on the due dates? Okay, so before we get into the second experiment, this is about Fresnel coefficient of an air glass interface. And I'm assuming, well, I know this has already been covered in the class in all the details. So we have changed the, well, this is after doing on my own the experiment using stuff in the kit. And then we have kind of modified a little bit based on our experience. So for example, there was this frustrated total internal reflection that we had put, but it seems that will be really difficult to do, or it will be very difficult to make any quantitative analysis on that, because the glass prisms that we are providing, that's not of very high quality. So we have accordingly modified this a little bit. So this I'll come back. So I just want to kind of quickly, so here, if you remember this I will cover also a little bit in the today. So getting the reflected intensity for S and P polarized light as a function of the incident angle, this needs to be measured. Then need to measure the Brewster's angle, and from that the diffractive index of glass, and then also verify that light at grazing incidence, that is theta about 90, is highly reflective irrespective of the polarization. Here there's a polarization selective reflection at Brewster's angle, but at grazing incidence, it's perfect reflection independent of the polarization. And also using a prism, we need to find some critical angle of glass air interface. Okay, so with this, any question, comment here?
So can the first deadline be extended by a bit?
And why?
So because like we got to know about the deadline just very recently, and some of us.
Okay, that's okay. That's I think fine. I will extend the deadline. Maybe we can combine the first two together. Will that be better?
So by first two, you mean that the first experiment in the both parts?
Yeah, and the second experiment, both we could do on next Friday. Will that be okay?
So we were thinking that maybe from Friday you can shift it to Sunday, so that.
So I was doing Sunday earlier. Maybe okay. So that's okay as well. I mean, this experiment number 1 I can do Sunday, and the experiment number 2 will be from Friday. Is that okay?
So actually, like in the weekend we don't have any classes, so we get a huge time span to perform the experiment without any interruption.
Is that what everybody wants? Is that fine with everyone? I can point
Anand,
out. Yes,
Anand,
Harsha.
may I say,
Yeah.
can we move it to Mondays? All Mondays they can submit rather than Friday, because then they get a weekend.
Well,
is that what they want probably?
Well, I think, see, if we get there, if they agree, I have no issue. We have no issue. But the only problem was let me just use this one. Let me just share my screen really quickly. Yeah. So there's I don't know if you can see my screen. Let me make it a little bigger so that you can see it. Yeah. So this midsem recess is October 9th and 17th. And this was my problem, you know. So if I put it on a Sunday or a Monday during a recess, will everybody be fine with it? Or somebody will go and complain that we have to submit something within the recess. So that was the only problem for me to shift it to Friday. But otherwise, I'm fine with Sunday or even Monday. I mean, that should be perfectly fine. So I'm taking that silence to mean that everybody is fine with a Sunday, even if it falls during the recess. At least somebody needs to confirm. Hello?
Yes, sir, it's fine.
It's fine. Okay. So then fine. Then I will shift it by, so 3 becomes, Harsha, you said Monday, no? 4, 5, 6. 6 September. Okay, I will shift everything by, and then this will become 13. And this will be 15. Fine. Any other comment, suggestion, question so far? Excellent. So,
Sir,
yeah.
what should be the content of the report?
Content of the report, no, the aims are clear, no, as to what needs to be done. For example, in the manual, in the lab plan that we have, shared, yeah. So measurement of the Heaney laser beam waste using a knife edge, and I did a detailed calculation of that and what needs to be done. And here for this experiment, it's basically from the lab manual. So all what needs to be done, it's very clearly mentioned there. Okay. In the Fresnel coefficients, it's again from the lab manual that we have provided. But again, there are a few things in the lab manual that cannot be done. So we have very, explicitly noted down what exactly are the aims. So these are the things that you need to show. Fine. And since we provide just a kit with very basic stuff, I mean, we are not really fixing how you would actually do it. You could be innovative and do it the way, I mean, everybody need not do it the same way, but these are the aims that one needs to kind of achieve and report in the lab report. Does that answer your question?
Yes, sir.
Okay. And we will again, as we proceed, we'll again modify these aims, more to the point so that it is kind of easier. But this is directly from the manual. All the aims are given, and this we have modified a little bit, for the things that cannot be done according to the manual. But again, this again, you will follow the manual, and wherever there's no manual, we will provide very clear, crisp aim. Okay. Right now we are at this experiment 2 only. Fine.
Sir, I think could you also clear up a little bit about what the contents of the lab report should be? As in, there should be an aim, a little bit on the theory and the data analysis, error analysis, and those kind of things.
Yes. So this is the aim, and then how you have achieved those aims. And then again, data, this is the regular lab report. I mean, but these are the aims. Since again, see, we are not providing a particular method. I mean, this is what you usually will have in a lab manual, that, you do this, you do this, you do this. But that part is not there this time because we have a limited set of, resources, and people will have to be very innovative as to how to do these experiments. So you do this with the resources that you have, or, any innovative ideas that you kind of implement. And then you just write in the detail as to how you got these results. Of course, a little bit of theory you will do as to what you want to achieve in the beginning, and then how exactly you have set up the experiment, what are the data you have taken, and you analyze the data, and then you show that yes, it matches with the theory, or it doesn't match with the theory. And if it doesn't, then some data analysis as to why it doesn't match, and things like that. So it's the regular stuff. Is that fine?
Yes, sir.
Okay.
So I think maybe Devaditya, I think the whole point is that do not fill up the lab report by the theory part of it. That is not the intent of the lab course. Idea is to focus more on what you are measured, what you got, what you analyzed, and things of that kind. Is that okay, Anand?
Yeah. And also this year, it is very likely that you'll be quite off from, what you get theoretically. So there should not be an effort at matching. There should be an effort. There should not be forced effort at matching the theory, but rather than the effort should be at kind of analyzing it as to why your data is not as good as it should be theoretically. Because we are working with very limited resource, maybe not of very high quality, but that is the kind of test with that. Even with not so high quality equipment, we sometimes we explore and understand physics much better than when it is very sophisticated and quite organized.
Yes, sir, that makes sense. Thank you.
Okay, so let me just quickly go through the concepts that maybe some 10-15 minutes I'll take. Let me stop sharing this. Just 1 second, hopefully it should work. Okay, I hope you can see my screen. Okay, so these are the things that this has already been covered in the theory part in all the details. So I'm not going to cover it, but I'll just kind of remind people as to what this is. So this is all about this is all about reflection at some interface, and here we are talking about some air glass or something like that. And then you have derived the detailed expressions for how when a light, from one medium with epsilon1, mu1, and the corresponding refractive index n1 goes into another medium with epsilon2, mu2, and the refractive index n2, what are these theta1, the angle of incidence and the angle of transmission and the angle of reflection, and how much it reflects, how much it transmits. This you have all done. So this is just quickly reminding all of that. So one concept that is there, again, this is refractive index, that's n1 sine theta 1, n2 sine theta, sorry, n1 and n2, these are the two refractive indices. The other concept is the polarization of light. Typically in quantum mechanics, we use horizontal polarization and vertical polarization. But when you're doing E&M, you typically do the P polarized light and S polarized light. So P polarized light is something that is parallel to the incident plane. For example, the light is kind of incident on this plane, it is reflecting. So the plane of this, my iPad is the plane of interest, and the electric field component parallel to that plane is called the P polarized light. So here the magnetic field component is coming out of the iPad, and this is the K direction. Now for S polarized, here we have the electric field component going into the screen, again going into the screen. So this component that is normal to this plane of incidence, that is called the S polarized light. So these are the two information this is covering. And then a few things this you have already done. One is this Snell's law. The Snell's law connects n1 theta 1 and n2 theta 2. This everybody knows, n1 sine theta 1, n2 sine theta 2. And here, if you want to calculate cosine theta 2, you just use this simple expression. And this I'm writing it in this way because I actually use it. then it is not that whatever gets falls onto this interface, all of that gets reflected. Part of it gets reflected, part of it gets transmitted. So what gets reflected, you can find that through this Fresnel coefficients, and then square of that, these are Fresnel coefficients, square of that gives you the intensity. So here we wanted to calculate the intensity of the reflected light. So light is coming like this, both the polarization. So how much of the S polarization gets reflected and how much of the P polarized light, the intensity, how much of that gets reflected, that you can find through this expression. Of course, the total transmitted and total reflected, that will be equal to the total intensity that came in. That will always be true. But for a given configuration, what is the reflected intensity in a P polarized and in S polarized? It is given by these expressions. Okay, so in these expressions, when you kind of look closer, what you find, there's few facts that you find. One is the concept of Brewster's angle. This concept is, you can see this is the of the light coming in, this is the P polarized light, this is the S polarized light. And if you analyze this P polarized light, this expression, you find that RP actually becomes equal to 0. And this happens when this particular condition is satisfied, that theta2, if that is equal to tan inverse N2 by N1, then RP is equal to 0. So this theta2, at which this, it becomes equal to tan inverse N2 by N1, we call that Brewster's angle, theta B. So the point is, at Brewster's angle, if the angle of incidence, now is it theta 2? No, this will be theta 1, is it? This should be actually theta 1, I guess. Fine. So at the angle when,
Yeah, it should be theta 1.
yeah. So at the angle of incidence at which you have this condition being satisfied, that we call Brewster's angle, and at that angle, if the light comes in at that angle, there is no reflected light. So here I have done a little cartoonish thing. So here you have light of unpolarized light. That means both the polar, whether unpolarized or some linearly polarized, but it has basically both the components. It has a P polarization and it has the S polarization. Both the lights are coming. Now at theta 1 equal to theta B, what you find is that this P polarized light, this component that is in plane, nothing gets reflected. But of the but in the transmitted beam, you will have definitely both the P polarized and some S polarized as well. But the point is, in the reflected part, there will be no P polarized light, and that is the definition of the Brewster's angle. The last concept that this kind of this lab covers is the total internal reflection. So this, I think you know from class 12, I guess, that when the angle of incidence is greater than some critical angle, and this critical angle is given by this formula, sin theta c equal to n2 by n1. If the angle of incidence is greater than this critical angle, then you have total internal reflection. This happens when n1 is greater than n2. So if the light is coming from a denser medium and going to a rarer medium, and if the angle of incidence is larger than sine inverse n2 by n1, then you will have the complete total internal reflections. So this is these are just the few concepts that this lab will try to kind of address. I also thought I will just give I mean, some of you might already have it, but for those who have not explored this way, it may be useful. I just did some very simple simulation in Mathematica. This will be just good for the visualization. Just get rid of this. Yeah. So this is a very simple Mathematica code that I've written. I hope you can see my screen. So what this is that this is again the same situation that I just were discussing. The light is coming from medium N1 and going into the medium N2. N1 and N2 are these refractive indices. And what I'm plotting, these are the intensity of the P polarized and the S polarized. Maybe let me just quickly share back. Okay, so here we have the light coming from medium N1 and going into medium N2. We have these expressions, the intensity for the P polarized light reflected and the intensity of the S polarized light reflected. And I just wanted to plot this RP and RS as a function of theta1. Again, let me remind you that this theta2 is already a function of theta1. So theta2 is already a function of theta1 by utilizing this Snell's law. So I will use this expression of theta2 in terms of theta1 right here. And so just plot RP as a function of theta1 and then change N1 and N2 and kind of visualize the idea of concept of the Brewster's angle. Okay, so here is a simple plot. I have both these plots I'm plotting together, and all I will do is kind of change the refractive index and see how the reflected light kind of changes. The intensity of the reflected light changes as a function of the angle of incidence. This x-axis is the angle of incidence. This one is the intensity. So let's say the refractive index is 1 and 1.5. Let's make it 1.5. So that's the air glass. So this is the typical curve you have. This one, the blue one, is the P polarized light, the intensity of the P polarized light as a function of the incidence angle. The yellow one or the orange one is the intensity of the S polarized light as a function of the angle of incidence. Now, if you increase the refractive index from, let's say, 1.5, I go to some 1.64. Again, this separation increases. This also increases a little bit. But you see the qualitatively, it remains the same. So for the S polarized light, for the angle of incidence 0 to 90, it continuously increases. But for the P polarized light, there is a point where the intensity gets to a 0. And then, of course, it increases again to catch up with the S polarized light at 90 degree. If I increase the N1, again, the qualitative feature remains the same. If the difference between N1 and N2 becomes smaller, you will have a smaller difference between these two curves, but the overall qualitative feature remains the same. And the point is that for this P polarized light, there is one point where the intensity of the reflected beam becomes 0. Now, if you actually go, let's say 1.5, and then I go past this, N1 is larger than N2. So then you see it is very similar behavior, but again, beyond some 65 or something, I don't have a data point. And the reason for that is the refractive, that angle actually becomes imaginary. So I don't have anything here. So this basically means that now you have totally internal reflection. It doesn't go into the other medium. It just gets reflected. So this is why, and hence there is no solution here. So that is what it means. But again, today we are basically going to do this 1 and 1.5. That's the air and glass interface. And for this, again, I just wanted to kind of keep in mind oops. Yeah, so you see this for N1 equal to 1 and N2 equal to 1.5, it's 56 degree is the Brewster's angle. Of course, for this one, I don't get any critical angle because it's N1 is larger than N2. When I do N2 is larger than N1, then I get a value for the critical angle. But you can see, you can calculate the Brewster's angle theoretically. It's like about 56 degree is the Brewster's angle theoretically. Okay, so I just kind of thought we'll do just simple demonstration to give a more intuitive visualization of these concepts. So I am done covering the concept part, and I can discuss a little bit as to how you would set the experiment. Any question here anybody has? Okay, so I'm assuming all good. So let me just try to see what I can do. Let's start this. Sorry, I'm trying to make it bigger. Yeah. Hopefully you can see the setup to some extent. Okay, I'm hoping that you can see the
Anand, you're giving away all the secrets.
well, so this is just for one or two examples we'll do, and then I think they have to be more okay, so this is what I've set up. Little bit. That's the again. This
So it is not visible.
Oh, it's not visible. Well, let me turn off the light.
So I think camera is not on.
No. Camera is very much there.
Yeah.
I have
You have to pin that. Anand,
yes.
Anand, can you give me co-host access?
Yes.
Then I can pin your thing and then it will remain.
Yes. You should have it.
Yeah, okay. So now I will pin for all maybe.
Okay. I think I have pinned it for myself only, I guess.
Yeah, that's the problem. Let me just see whether I can pin it for all. Okay.
That works?
I'm unable to pin it for all, I think.
I think everybody needs
Sir, you can spotlight the video. You can spotlight. Then
Where
it
is
would
it?
be pinned for it. It's in options.
Settings.
No, not in settings. Beside beside Ananja, there will be some arrow. If you click on that, you will get the spotlight for everyone option. In the participants. If you
Participant
click.
list. Okay.
Oh, spotlight video. Okay.
I'm not able to.
Is that fine?
Yeah. Anand,
Yeah.
I'm not a co-host yet.
Oh, I see. Hang on. Man.
And you need to mute yourself.
Yeah. Can you hear me now?
Yes, we can hear you.
Okay, fine. So make co-host. Yeah.
Yeah, now I can spotlight your.
I think I've already done that, hopefully.
Okay. Yes, I hope everybody can see.
Okay, so again, yes. Okay, fine. Thank you. So this is just one way of doing things. Again, there'll be different ways of doing things. So here, I just printed a, oops. I just printed a sheet of paper with all these angles I have written so that it's easier for me to align. And then I'm also, using this red line you can see here. And again, if I am exactly on top, this red line is aligned with the black line, which is my 0 in this protractor. So again, since all this arrangement, because we need to take the angle measurement. And then again, we don't have any apertures or anything as in the lab, so we have to be kind of innovative as to find out if if these angles are correct. For example, I would want the laser coming out of this, the light beam coming out of this laser to kind of go exactly along this line. So, I mean, I can show you one way in which I will kind of ensure that. Then I have this glass slide mounted on this clay dough, which will be, again, you can see if it's become a little dirty. So I haven't cleaned it, but I think with some methanol, or just simple water, or this spray that you have in Colin or something in the household, you can actually clean it. And then I've made a simple screen. This is the bookend. Just tied with 2 rubber band. It's a piece of paper on a cardboard. Okay, so that's the simple experimental setup. So I'll put my camera here. Okay, so let me turn on the laser. Okay. Now I wanted to make sure that my laser is going this line. So, I mean, one way you could do it, you just put a scale, vertical scale at the beginning of this line, and then you see that, yes, it is actually, just because it touches, I know the light is, going through that line. And then I'll put a scale at the end of this line, and then again see that it kind of touches. Fine. So this says that my light is aligned on this line here, this to this, and that defines my 0 degree line. Okay. Now I know that now that this laser is following this line, and now this is the glass slide that I have. Now I want to put that make sure that this glass slide is at some angle to this incident beam, and then we want to see how much is the reflected part, how much is the transmitted part, and then make the intensity measurement of that part. So for that, I just need to put this glass slide at different angle. So I have made some marking, not all the markings. That is, all the markings are not possible. For example, I'm putting it at 30 degree. Let me just kind of try to show you how I'm doing it. So if you see from top, that's my 30 degree line. And then you can see if I'm perfectly on top, then you see this glass slide aligning to that 30 degree line to some very good extent. And as I said, this light, as you can see, if I put my scale in the beginning of this line, it touches, you put it in the end of the line, end of the line, touches again. Okay, that means my laser is aligned to this line here, and my glass slide is aligned to this 30-degree line here. So all I need to do is just make this glass slide at different angle. And again, the markings I have, these are for 10, 20, 30, 40, but there could be other methods as well. I mean, you can rotate the glass slide, and then whichever orientation it is, you can draw a line with a pencil and later actually measure what angle you put it at. So it need not be before you do the experiment, it could even be after. But again, as I said, this is just one method that we are showing. The whole point is that this anyway is a straight line, the glass slide. Laser will remain a straight line. And so you can, each time you take data, you can also just draw a straight line with pencil of the laser and the glass slide and find the angle that way as well. Okay, but this is just one way. All right, so now you can see that with this, and here is a polarizer I have. So this polarizer is such, you can hopefully see it. This polarizer is such that it lets the P polarized light and it blocks the S polarized light. And that is what we want to actually check. For the Brewster's angle, we need to see, you know, I mean, the P polarized light has to go to a 0. Well, with these kind of polarizer, it won't go to 0, but it has to show that there is a minimum. It decreases and there is a minimum as a function of angle of incidence, and then it increases again. So now if I rotate this, now I'll move my camera so that you can see the spot over the screen. You can't see it from here, so let me move it much closer. So hopefully you can see it now. So you can see the glass slide as well. Okay, so without the glass slide, you could see there is a spot on this wall. So that is a transmitted part, and there is a spot on the screen, and that is a reflected part. This one is a transmitted. This one is a transmitted, and that one is a reflected. Okay, and we just want to focus on the reflected part. And this is my polarizer. Let's see if I can do it. So you see, it's quite, you probably gone outside the range. Yeah, so it's a very intense light. And then if I go in the other direction, it's still okay. Now you see it has decreased. I don't know if you can just. And this is a tiny point I want to kind of focus. This should ideally be 0, but it won't be 0. You see, kind of, that's the minimum thereabout. And then if I tilt it more, the glass slide, when it starts.
Anand, if I may comment,
Yeah.
actually because of the oil film on your glass slide, there is much more scattering. So you will probably, unless it is very clean, you will not probably see enough minima.
That is also true. And then maybe just let me just clean it.
Yeah, or you can just replace it with the other one, another one, fresh one. That might improve it.
Sorry, cleaning was much faster. And then also this this polarizer is not a.
Of course, yeah. Polarizer is of course not that great.
You know that it is 0. Yes, we can see some reduction in that speckle pattern kind of. Now it is actually, thank you. Now it is much better. So this is the minimum. Let me just bring it closer. This is the minimum that we can get. And then if I increase it either in this direction, you see it starts increasing.
It's increasing, yeah.
I'm just moving the screen and my polarizer together. If I rotate, this is kind of increases. If I go back, this is almost the minimum now. And beyond this, so this is still decreasing, and then beyond this, it will start increasing now. Okay, so this I would say is the kind of minimum. Now let me just show you approximately. Again, this won't be exact. This is the minimum. So let me show you. This is right around where I have what? 30 degree, 35 degree maybe. 35 degrees. So what is the angle of incidence? 180 minus maybe around 40. So 180 minus 40 is how much? 140. Half of that is 70. Should have been around 60. So probably that is not perfect.
Anand, may I suggest something?
Yeah.
Actually, if you put in the light to be, horizontally polarized from your laser, which is unpolarized, you might get a minima, much better minima. So I'm saying you align the input, with which is horizontally polarized. I mean, in the plane.
Depolarized.
Yeah. And then you measure the minima, it'll suddenly go down to 0. Because our laser is unpolarized, right? So
no, you can see that. So this, again, the polarizers are not perfect. So now what I'm doing, oops, I put my phone down. Sorry about that one. So what I'm doing now is putting a polarizer right here. So this is supposed to get the P polarized light out of this laser, which has P and S both.
yes.
So after
And now,
it is basically polarized, and that is hitting the this glass slide. Of course, I have a transmitted component that goes all the way to the wall, and then I have the this reflected component that gets here. Now let's see if we can reach 0.
Yeah, 0 might be easier to. Yes, it went through already.
Yes.
Yes, there. Just prior to that.
Now it increases, comes back, almost 0, but minimum. And then if I start moving it,
correct.
You have to move this. So this very clear. So I think this will be a right way of doing it. Then you can
Yeah.
select one polarize the P component and get the plot. P.
Yeah.
In,
I think, Anand, what you asked them to do, which was to plot both S and P. I think they did do the experiment independently. Plot at all angles, and you will clearly see the Brewster. Not an issue.
yeah. So this is for P, and if you wanted to do it for S, I think
You
you
just rotate it. Yeah.
just quickly do it. And then we'll see that hopefully there is no minimum in that case.
Yes. There shouldn't be any minima. Yeah.
So now flip this, change the orientation of this polarizer, and this should now let the S polarized. Yeah, then this should also be S polarized. Now if I rotate, you don't see any minimum. It is. So again, this is probably a better idea.
Yeah.
So polarizer so that it selects just P or just S, and for that, this is P. This should also be P. This is also should be S, and then that way you can get the intensity for the P polarized and the S polarized as a function of theta. Once you have it, then you fit it with the theoretical function, and then through that you can find the Brewster's angle and then also the refractive index of the glass. The other thing that we asked that, at almost, this is just to show that grazing incidence, for example. Again, this experiment we are showing in detail. Again, I won't be doing this detail every experiment, but I thought at least one we should do. At the when it's a grazing incident, then everything gets reflected irrespective of polarization. And so you see when it's near normal, I mean this is not near normal. Sorry. This is near normal, then most of light gets transmitted. But if I go near grazing, to the extent that I can do it, you see these two spots, that's my reflected spot, which is very intense. It's more, although this you can't see through the spawn, but this is much more intense than this. So
And the point.
yeah.
Yeah, and the point is that if you now rotate the polarizer, they'll be comparable.
Yes, and then
It will be independent of the angle.
Then there is no dependence on the polarization either. It will have the same weightage. So this is for one polarization. This is for the other polarization.
Slight difference, but not too much. And then that is because of the scatter on the polarizer itself.
I didn't do it properly.
Yeah.
So I need to put the polarizer in both the places. So this is one polarization. This is the intensity, and if I do the other way.
So by the way, a trick question for everybody. So when you make the Ray-Ban glasses, what do you think should be the polarized? These are polarized glasses. What should be the orientation of the Ray-Ban glasses polarizer within the glass so as to cut out the glare? Right? People can think about it. That will be interesting. With the grazing angle, you should be able to answer that.
Yeah. Okay, any questions so far? So I think I am done of the 3 aims that we had, or the 4 aims we had. Let me just check. Brewsters, verify the grazing index is highly reflective, and okay, and then you can also do a critical angle of glass air interface. This is I tried. I think this is a. I'll show you. This is also exciting for me. So this is the prism that we have. And then in the prism, I mean, again, I can put it like this.
You above the critical angle? You probably are, right? Is there any transmitted beam there? I can check it with the.
Oh.
Yeah, perfect.
Yeah, let me just try to show the. Yeah. You can see my. You can see the red. Although it's a green laser, but you can see this red. This is essentially scattering, so don't worry the color. So this is the light. So this is when it kind of transmits, but when it starts just total internal reflection.
There is a question from Kalash Talati.
This is the totally
Yes.
So now at this point, I will have nothing on my wall. So it's all dark, so you can't see. So here is my reflective spot, and there's nothing in the
Now you.
And if you actually want to measure the angle of reflection, I think if you put this the prism on a nice lining, you can actually get it. Let me put it
We can actually see the scattering through it. Yeah,
yes.
It's very nice.
So that was the exciting part. So if you align it properly to the line, you can actually find the angle very easily. Well, the angle will be half of the whole angle. That
Yeah.
you can actually see. So total internal reflection, and if I increase it, there's nothing. Now it is total. It's kind of going this way, and now you can. It's going that way because there's a refraction. Okay, so I think that's it. Any question here?
So in chat there were how do we know which is the orientation is S polarized? I think that is a question that you should answer yourself. Okay, can you hear me?
Yeah, who had that question?
Exactly, Devaditya, that's the answer. We can use the same experiment to determine which is the S polarized and which is the P polarized. Yes,
Yes.
that is correct. Good one. Yes. Anything else? Very nice. I think Anand, we didn't intend this, but the fact that you should not touch the optics and your hands are oily because of the Play-Doh and we can spoil every experiment and every optics is a very good lesson.
Yes.
So thanks to Play-Doh, we are kind of re-emphasizing it a bit too much. You have to keep cleaning the surfaces. All right.
Anytime you see too much scattering speckle, that means there is enough dust or oil on the surfaces. Yes.
Yes.
Any other question?
Somebody asked whether they can use a broken slab. Yeah, go ahead, be my guest. Where do you get a glass slab? I don't know, but if you have, use it.
It doesn't really matter. I think you just need to be, I mean, I'm orienting it this way, for example, but I can really do it this way as well.
Yeah.
So with broken glass, just make sure that you don't cut your fingers, but otherwise, it's okay. So, any other question?
So, can you tell what we explicitly wrote in experiment 1? I got the data very fluctuating, not getting perfect omega in first experiment.
Fluctuating and not getting? I didn't get the word.
Not perfect omega, basically frequency. Sometimes it seems periodic, after them it became aperiodic and quite random.
No, but why do you expect a periodic signal? I don't understand that.
E की power I omega t is function.
Arey mere bhai, that is the whole point. Are you measuring e की power I omega t? That omega is 10 to the power of 16 or 14 hertz. You can't measure that.
Okay.
What you are looking at is that is the whole point about the experiment. You see that the amplitude of your laser is fluctuating in time. Well, E is
Yes, sir.
fluctuating in time, not e to the power I omega t. Omega is 10 to the power of 14 for this optical light. You can't see that, isn't it?
Oh, yes, yes. So
So
what we have to basically plot the graph and take
plot
average
the
and variance.
graph, look at average, calculate the standard deviation, then put an error bar on the graph telling you that this is the fluctuation.
Okay.
Right? Now let us say you do this. Now let us say you do this experiment, which is with the Brewster angle, and then sometimes you get a 0, sometimes you get a little more. There is an error bar to that as well, because the input laser itself has got an error, right? So that
Yes.
error is going to be through intensity variation is constant, literally all through all the experiments, and you're just trying to quantify it. That is the whole point. Is that okay?
So what does mean error bar? I don't understand.
Error bar means there is a value. Let us say the value is 100, average value. It is fluctuating now about 100.
Yes. Yes.
Now you're asking how much is the fluctuation?
Variance.
So the
Standard deviation.
exactly standard deviation. So the size of the error bar, that is, you plot a point, which is the average. On the point, you put an bar, right, which has got a size. That size is the variance. Tells you that the value is within that bar largely. Statistically, it will be found within that error bar. It is not an exact value of 100. It could vary from, let's say your variation is variance is 10. It can vary from 110 to 90. That is the value. That is what you mean by error bar. Haven't you seen graphs with error bars? Oh, probably in school you have never seen a graph with an error bar. That I agree. But look at any book, anything, you'll see experimental measurements with an error bar, a point
Okay.
and a bar around it. Okay.
Okay, sir. Thank you.
Yeah.
So somebody is asking, is the red color inside prism due to IR rays which are used to produce the green laser? No, green laser is green, it should be green, but I think the red laser is a scattering. Scattering happens at different wavelengths than the wavelength which you kind of excite. So it is the scattering, the scattered light.
So I think that is, yeah, in other words, that is some impurities in the glass. If the glass was very pure, you won't have seen it.
Yes.
That is what you need to make it for, let's say, a fiber. For optical fiber, you need to remove all the scattering. And the guy who removed all the scattering got a Nobel Prize, by the way, just in case you want to know.
Yes.
I was guessing for this question as polarizer is a sense long, closely spaced strings. Okay. Yeah.
Okay. Any?
Closely springs. Maybe you want to take that or I should finish that.
No, I am not seeing that. Probably that has been
Chat.
sent private.
It's in the chat.
No, I think that has been sent to you privately. I don't see that.
Really?
It looks like, because I don't see.
Oh, it's a direct message to me. Oh, sorry. Hey, man, may I request everybody who's asking a question to ask publicly, yaar?
Yes.
We are not running a private show here.
Unmute yourself and speak. I mean, there's no need to type.
No, but somebody has asked a question. Let me just read the question for everybody. I was guessing for this question as a polarizer, is it a sense of long, closely spaced strings? So it will diffract laser, but the spread of the diffracted light would be greatest only at the polarization transmission. So there is a difference between diffraction and a polarizer with a long, closely spaced strings. I think this is a topic that I would urge all of you to explore. Thank you very much for putting this out. Jagdish Chandra Bose actually did this to show that the beams were polarized. Okay, and he made the polarizer with indeed closely spaced wires. But let's say if the wires, so what is the difference between diffraction and a closely spaced wire, right? That those scales one has to think about. So I'm not giving the answer, but it is a very interesting, it's in the right direction. Anand, you want to add something to make it more?
Oh, I think let's keep it at that point.
Yeah, they keep it at that. Yeah, fine.
Curiosity of yes.
Yes, yes.
Yeah.
Somebody has said that the laser is using IR diode inside. Mm,
No, these
probably.
I think there are a few comments. There could be whatever inside the laser, but what comes out of the laser is the green laser. And
Yes.
so then, but what you see, you never look into the laser. I'm not suggesting anybody does that. Nobody looks into the laser. What you see is always the reflected or the scattered light. Now, what gets reflected, how it gets reflected or scattered, that depends on the material which is scattering. So what you see is the scattered light, and how the wavelength changes in scattering. That's a huge thing, another Nobel Prize winning thing. That you could study, but it is not because of somebody's using red IR diode inside the green laser, hence we are seeing it red. No, that is incorrect. Any other question?
Mayank, you're talking about which question? The polarizer question or what?
Yeah, the closely spaced.
Yeah. So he's asking how is the polarizer made? Is it made of closely spaced wires? Because closely spaced wires will diffract, right?
Yeah.
Yeah. So what do you mean by closely spaced? That is where the answer is. Whether and at that scale, whether you want wires or you want, like Aditya says, stretched molecules, that is your problem. And we will leave that at that. I want you people to explore that. The difference between diffraction and making a polarizer with stretched wires or molecules or whatever.
Okay.
Is that okay?
Yeah.
Any other question? Okay, so if no further, we can stop here. I'll put it on the course webpage by evening or by tonight.
Okay, great.
Bye.
Yeah. Thanks, Anand.